Now you can see that it's moving. It's solving the inverse kinematics continuously at each point of time. With the help of Kinematics and Dynamics Library, I have a file and it makes a tree of your complete robot. Okay, so the tree is a global view. Solver, there is a function called as join to cart. So it will take joint angles and it will update pose variable. It will make a tree, it will make chain, it will make segment, it will make joint, it will initialize solvers. Everything this function is. I'll start. See, it's solving the inverse kinematics with KDL only. I have not. Welcome back to my channel FusyBots. So today's topic will be very interesting. So if you are working in the field of robotics, especially in the field of manipulators, sometimes you have felt that solving the kinematics like forward and inverse kinematics for the manipulator becomes a bit complicated with the help of analytical solutions, or we have n types of robots. So if we are working on different types of manipulators, then every time we have to write the kinematics for that. So a question may come to your mind that can we solve the kinematic without actually doing all those mathematics, the complicated mathematics by ourselves? So yes, there is a way to do that. So the today's topic will be that only, that is how to set up the kinematics and dynamics library for solving the kinematics of a serial chain manipulators. So this KDL library is basically maintained by ROS, and this helps you solve the kinematics of serial chain manipulators. And we can use this both in Python as well as C++. And I will help you to integrate it with ROS2 and make your task easy. So let's move on to the video. First, uh, first I will show you how I have used it to solve kinematics of Franka Panda robot. So yeah. So this is my Franka Panda robot, and this is a 7 degree of freedom robot. So I have used KDL to solve the kinematics of this robot. I can just enable it, and when I try to move it, now you can see that it's moving. It's solving the inverse kinematics continuously at each point of time. So that is with the help of Kinematics and Dynamics Library. I have not solved the complete kinematics of this. Now by the end of this video, I will also show you how can we use it to solve the inverse kinematics of our custom robot or with any 6 degree of freedom robot. This is my website FusyBots, where I have published a blog, a complete blog where step by step everything is there. Now I'm going to explain you how it all works. So let's start with the first thing. So for solving the kinematic, there are two methods basically. First is the analytical method, second is the numerical method. Analytical method gives us a closed form solution, whereas numerical method does not give a closed form solution. So what do we mean by analytical solutions? Analytical solution is basically we have n equations and we have n constraints, and we can just solve those algebraic equations. So for suppose we have equation y is equal to mx plus c. Now if I have two values on a line, I can find the equation of line. Similarly, we can do the analytical solution of our 6 degree of freedom robots, because we have 6 Cartesian positions x, y, z, rpy and 6 degree of freedom robot. In that case we can do it because that is a completely solvable system of equations. Now what happens if we have more degree of freedoms, like if we go to 7 degree of freedoms, or we have less degree of freedoms, like we have 4 degrees of freedom? In that case it sometimes become complicated. So we can use numerical methods for that, and you must have studied some of the numerical methods, like we have Newton-Raphson method, we have least square method. Okay, so these are some of the numerical method, but the main thing with the numerical method is that you have to start with a very good initial guess. If you are not starting with a good initial guess, your solution will not converge. Either it will go to a completely blunt solution, or it will stuck in local minima. So I have also dealt with this problem in my code. I will tell you how like I have dealt with it. Now prerequisites for KDL. Before starting with KDL, there are some terms which are being used in KDL. I will tell you what are those terms and then we'll move forward and try to implement it. So there are three terms. First is tree, then there is chain, there are segments, and there are solvers. So four terms are the main. Okay, so what is a tree? So tree is basically complete representation of your robot. How tree is made? Tree is basically made from your URDF file. So it reads your URDF file and it makes a tree of your complete robot. Okay. So the tree is a global view. But when it comes to chain, a chain is basically a path from the starting link to the ending link. So for suppose I want to solve the kinematics of my robot from first link to sixth link. So I will give, okay, this is my starting link, this is my end link. Now it will make a chain of all those links considering all the joints in between them. Okay, so that is a chain, and we are always worried about our chain because the kinematic solver is working in this chain. Then comes segments. So a segment is basically a single piece of chain and it represents a rigid link plus the joint that it connects to the next link. A segment show you how it looks like, then it will be easy for you to understand that. So it basically consists of joints. What different kinds of joints I have? For suppose I have revolute joints, I have prismatic joints, I have continuous joints. So in segment we all have that. Okay, now we have solvers. What are solvers? So for solving the forward kinematics and inverse kinematics, we initialize different kind of solvers. So I will show you how that works. First, I will show you how can you convert a URDF to a KDL tree. So there is a function for that, that is KDL parser tree from string. Using this function, it will take your URDF and it will convert it into tree. But the question is how the tree structure looks like. So this is the tree structure. Now, I also want to show you my URDF. On the screen, you can see my URDF for my custom robot. So this is my custom robot and I have made a URDF for that. So it's starting from base link, then we have some joint J0, then we have another link L0, then we have another link J1. So this is my complete URDF. Now, this function will read this URDF and you can see it has made a tree. So the root is base link. So in tree there is a root and then there are childs. Then it has made different type of childs of it. So base link is the child, then there is a joint, then there is a segment, then there is a joint. In this way you can see it comes to an end and it has taken into account all the segment, all the axes, joints, everything. Okay. Okay, so now we have KDL tree. KDL tree is basically passed from URDF. Now from KDL tree we'll move to KDL chain. How we get KDL chain? We just give the starting link and the ending link and it will extract the chain from it. How does that chain looks like? So you can see this is my kinematic chain and it is from base link to LE1. So I want to solve the kinematics from my base link of the robot to the LE1. So I have given that in the input. You can see here. This is the function in the C++ that we call. Now this is the chain. Now in chain you can see there are different type of segments. So basically it has divided my links into segments. That is, there is a L0 segment which has joint J0 and that joint is fixed type joint. Similarly, I have L1 segment that has joint J1 and it is a rotational axis. If you take it, if you take the analogy from the URDF, you can see my base link. Then my first is the L0 segment. L0 segment, then J1 joint. Then I have L1 segment. Next joint, that is a J dummy joint. Similarly, it will make a chain out of it. Now the main thing, it is a very important thing using the KDL library. So while using the KDL library, it parses your URDF in one way, and your joint states where you are publishing the joint values may be in a different way, like somewhere you have done a mismatch or something like that. So for that case, you have to collect the joint names from here. You just to make sure that J1 values correspond to the actual J1 of my robot, J2 correspond to the actual J2 of my robot, so that there is no wrong values that are going to any of the joint. And the next main thing is to skip the fixed joints, because in the fixed joints we will not be giving any values. So before passing this chain to my KDL solver, I will have to skip these things. Now, so just remember this point. This is a very important one. Now, set up KDL solvers. This is one of the most important things. So there are different type of solvers in KDL. There are FK solvers, there are IK solvers, and there is a recursive solver, which takes both FK solver, IK solver, and recursively finds the values what you wanna take. So there are n types of forward kinematics solvers. So I will not explain each and every solver. You can also go to the documentation of Orocos that I have given in reference, or you can go through my blog. You can, like, I have given the proper explanation of each of the solver. But what a FK solver will do, FK solver will take the joint angles and it will give you the end effector position. That is what FK solver is doing. Then what is IK solver do? IK solver takes end effector position and gives you joint angles. But here the hack is IK solver also takes the initial guess. Now, how to get this initial guess? That is one of the most important question, because we want a solution to converge. Okay, so now IK solver may be of many types, like we have velocity solvers and we have position solvers. I have given a detailed explanation. You can just go through the blog once and you will be clear about that. Okay, now how to solve it? So FK solver, there is a function called as join to cart. So it will take joint angles and it will update EE pose variable, in which it will update the end effector pose, that is in K, that is a KDL frame type variable. Similarly, how my IK solver will work? It is, there is a function cart to joint. It will take Q init, that is the initial guess, that will take the end effector position, and it will give you the output joint angles, like what is the joint angle corresponding to this end effector position. Okay, so this is how KDL works. So it is very easy to set up KDL for any of your robot. You just want to have a URDF, but make sure in URDF you maintain the proper link names. You properly maintain the hierarchy in the URDF. If URDF is correct, 70% work is done. Now we have to make sure these things works fine. Now in this you can see I have shown using KDL for different type of robots. So one is a UR5 robot. So I have used it to solve the kinematics using KDL. One is a Franka Panda robot. So UR5 is a 6 degree of freedom robot. Franka Panda is a 7 degree of freedom robot. For both the cases it will work. Okay, you just have to provide the constraint, you just have to provide the solid initial guess, then your work is done. And I have also made my own custom robot that I already shown you in many of my blogs and videos, and I have applied KDL to this also, and it works for my robot also. I will show you the video after some time for my robot also. Now, there are some of the frequently asked questions. You can go through it. You like, these questions will also come to your mind, so better to go through it first. Okay, we'll move to the code, like how I have written it in the code. Anyways, I have explained everything in this blog, but still, just for a quick recap, I will show you my code, how I have set up the KDL in my code, and then I will show you how I have set up KDL for my custom robot, and I'll show you if it works or not. Okay, so coming to the code, how I have set up in the code. So to set up in the code, first I have written the init kinematics function. So what init kinematics function will do, it will take the URDF. It will take the URDF from you. It will make a tree, it will make chain, it will make segment, it will make joints, it will initialize solvers. Everything this function is doing. This is a very simple function. And you can see this all I have explained it in my blog. Okay, so that's a very easy thing. After doing all of this, then I have two functions. One is a get end effector pose, that is my forward kinematics function. Another is get joint angles, that is my inverse kinematics function. And inside this, it is just calling this function only. So it's a very easy thing. I have already explained it in my blog. Secondly, this is my inverse kinematics function, and it is also same. You can say this function I already showed you on my blog. Now there are one and two important things. Like, first is, what is the initial guess I am giving to my inverse kinematics? That is one of the most important question. Second question is, I am giving the URDF to my init kinematics function. From where this URDF is coming? So I will show you both the things. So for getting the URDF, so you know that there is a robot description topic, and the robot state publisher basically publishes the entire URDF to robot description topic. So we can take use of that. How I have done it, I have subscribed to robot description topic. So you can see that this is my subscriber to robot description topic. Okay, so as soon as it subscribes to robot description topic, it calls a function. You can see. So what this function will do, it will take the entire data from that robot description topic, because it publishes the URDF in the form of string in that topic. Now I have my entire URDF in this string. Now I can directly pass it to init kinematics function. Okay, so that's very easy. So yes, we also have init dynamics function. We can also solve dynamics with the help of KDL. That we'll explore in some other videos. Now the second most important question is, what is the initial guess for my inverse kinematics? So my initial guess for the inverse kinematics will be my current joint angles. So for example, I want to find the inverse kinematics for I plus 1th and effector position. So I will give the ith joint angle as the initial guess, because that is the closest one. In that case, it will always converge, and I have used this concept in 3 robots: Franka Panda, UR5, and my own custom robot, and it works for almost all the positions. It always converges. So you can see whenever I am passing the inverse kinematics function. So I can show you where my inverse kinematics function is. Yes, so in my execute, you can see whenever I am passing the inverse kinematic function, you can see that I am also passing current joint states. Okay, so I am always passing current joint state because that is my initial guess. So this is how it all works. Now I will show you the video of my custom robot. Then it is solving the inverse kinematics with the help of KDL only. I have also written the analytical inverse kinematics. I have made a video for that and a blog for that. You can go through that and understand how we solve the analytical inverse kinematics. But for easy thing, we can also use KDL. Now I will show you that. So I have launched my robot. So you can see on the screen the RVs. Then this is my custom robot. So I don't have STL files for it. So I am just showing it on the RVs. So I'm updating the status now. For suppose I want to, so this is joint actually, it's just written as joint. These are actually Cartesian position. So for suppose I want to go 0.23 instead, I'll start. See, it's solving the inverse kinematic with the help of KDL only. I have not written, I have not used the analytical inverse kinematics here. I want to go 0.35. Now again I want to go to 0.45. You can see it went. So that is how our task become very easy with the help of kinematics and dynamics library. So okay, I think this is the end of my video. So I think you have understood how can we use the KDL library, how can we set it up with our ROS2 environment and use it to solve the kinematics of our robot. To extend this, I also want to say that we can also use the KDL library to solve the dynamics of our robot, but that we'll cover in a separate video. So if you like the video, if you understood the topic and my video helped you in any of the ways, so hit the subscribe button, like my video. See you in the next video. Thank you. Bye bye.